Okay, we are going to do section 5 notes. Well, it says, okay, so it says section 4 right now. I'm going to change that. Should be section 5 notes. There we go. So you may want to change yours too, because I'm sure yours says section 5. Okay, let me, this a little bit larger. Okay, so the first thing I'm going to ask your classmates is to look at this picture of the water molecule and what two molecules would we split this into. So basically, if I can break this water molecule in half, how can I break this in half? So, I can either break it here or here, right? So if I choose to break it right here, I have a hydrogen and an OH, right? Now if I chose to break the other bond, if I break this bond, I have a hydrogen and an OH. So no matter what, I'm breaking this water into a hydrogen and an OH. So it says, so let's write the equation for this below. So what I have is I have H2O, and I'm going to do this, and now this is what's called a reversible reaction, which means that I can make the products of hydrogen and OH, but I can also then go backwards and make water from those also. This is happening. Now it happens, doesn't happen a lot. So if you have a cup of water sitting there, it may happen twice for every like billion water molecules. So it's not happening a lot, but it is. Every now and then a water will break apart, but then as it breaks apart, another one will come back together. So which product represents the acid in the above equation? And which product represents the base? Well, we know that hydrogen, this H plus, that always represents an acid. And in fact, a lot of times that H plus is synonymous or the same as saying H3O. And then which product represents the base in the above equation? That is going to be my OH. So here's the thing, is how I said hydrogen is sometimes the same as H3O. What we will get is we will get two water molecules doing this. And so what happens is you do get H3O. So one of these water molecules takes a hydrogen from the other water molecule. So let me draw that out so maybe that makes a little bit more sense. So I have two water molecules, and this one takes that. So now I have H3O and I have an OH. Okay, so that's what's happening there. So which product represents the base? That's going to be my OH. So remember, this H plus is really kind of like H3O. They're synonymous, they're the same. All right, so when one water molecule, when one of them breaks down, it produces one hydrogen and one OH. So then at this point, each time when this breaks down, I get an acidic particle and I get a basic particle. So what would you think that would happen? Would that be an acid then? Would it be a base or would it be neutral? Well, if I see that I'm getting one acid molecule and one basic molecule, I'm going to assume that that's going to be neutral. So I'm going to say that that is neutral. So every time that this happens, every time I have a water break down or steal this hydrogen, there's my acid, but there's also a base. It's always the same. I can never, if it's just pure water, I'm never going to be more acidic because every time one breaks down, you get an acid and a base. So you're never making more acid than base. It's not possible. Or the opposite, you're never making more base than acid. It's just not possible. Right? So let me clear that. Okay, it says, will the number of these two products always be equal? And that is yes, and I just explained that because when H2O breaks down, you make H plus, which is my acid, and OH, which is my base. So it's always making an acid and a base at the same time. So it's always going to be neutral. Some questions to research right now. So I'm going to have them get their computers out, and I'm going to have them look up how often do water molecules ionize. So I'm going to do that on my computer right now so you can see what the answer would be. Let me pull this over here. So how often do water molecules ionize? Yeah. So if I look at this, it says random fluctuations in molecular motions occasionally about once every 10 hours per water molecule. So if you're sitting there looking at your drink, if you had like this water bottle of mine, it has been in here for 10 hours. So in 10 hours time, they have like one water molecule has broken down and come back together. All right, another one that I've seen as I've searched this is, I'm trying to think. It was like something about 2 in every million or something like that. I can't find it, but that was also another option I saw. All right, the second question, what is the equilibrium constant of water at room temperature? So, what is the equilibrium constant of pure water? Room temperature is about 25 degrees Celsius. It's about 77. It's a little bit warmer than room temperature maybe, but it's about 77 degrees Fahrenheit. So if you look at this, it says this equilibrium constant will be 1 times 10 to the negative 14. That's going to be important. So I'm going to write that down on here. Let me clear that out. All right. Bringing it back over here to the board. And it's going to be 1 times 10 to the negative 14. Now, they will call this Kw. That is the concentration of, or the equilibrium, when water is at equilibrium. Okay, the equation that I'm going to write for this is Kw equals, OH times H3O. Okay, it's always how much of this base do I have, how much of this acid do I have, and they're always going to equal 1 times 10, because Kw equals 1 times 10 to the negative 14. So another way to write this is 1 times 10 to the negative 14 equals OH times H3O. Okay, so what we know about the equation from above. How many H molecules are there at room temperature and how many OH molecules are there at room temperature? So here's what I mean by this. So at room temperature, when everything's at equilibrium, when my acids and my bases are equal and everything is good, I would figure this out by saying, okay, well, I have something, it's almost like saying these two things are going to be the same, right? They're at equilibrium. So this number will be the same and this number will be the same. So it's almost like saying x times x, right? Or x times x is x squared. It's almost saying like x squared equals 1 times 10 to the negative 14. So to figure out x, I'm taking it back through some algebra here. Bear with me. I'm going to take the square root of this, right? So the square root of this, when I do this, if I do this math and I take the square root of 1 times 10 to the 14th, it tells me what each one of these should be when it is at room temperature, right? This can change. Like this number right here can change if I raise my temperature, if I decrease my temperature. But when I plug this in, it's 1 times 10 to the negative 7 for each one, right? Because they're the same as when hydrogen goes, when OH goes. So they're going to be the same in pure water anyway. So I say this is, remember, we're dealing with pure water right now. We don't always have pure water, and this OH will be different than this H3O. All right, so we're just looking at pure water. All right, clear that out. All right, so neutral solutions will have equal amounts of OH and H3O, just like my pure water at room temperature. Now, if I have an acidic solution, we're going to have more H3O than OH. Basic solutions will have more OH than H3O. Now, the notes aren't until tomorrow, so I had just kind of done my preliminary note-taking here and making the notes. So I want to pull something up real quick. This is the picture that I was going to add into this, but I hadn't yet, so I hadn't printed them off for your class yet. So let me pull that up. I'll show you what I'm talking about here. So this is a visual showing what I just wrote down. So this is the image that I was going to use. Look, here is my neutral solution. This is pure water. My H3O and my OH are always the same. This is, once again, at room temperature. Now then, if you look here, an acidic solution at room temperature, you can see where my H3O is a lot higher. And then if you look at my basic solution at room temperature, you can see that my OH is a lot higher. So this picture, I'm actually going to go ahead and add it while I have it there. I was going to add into the notes. So, ooh. Sorry, bear with me here. All right. All right, so there's that picture then. All right, so calculating H3O. What is the H3O if OH is 5 times 10 to the negative 8? So this is what I'm going to do. Let me get my calculator ready. So I'm going to say, okay, well, I know that 1 times 10 to the negative 14 equals OH times H3O. So by the way, they're going to be able to write that down on one of their little sheets. So just keep that in mind. So now I am just plugging this in. So I know 1 times 10 to the negative 14 equals 5 times 10 to the negative 8 times H3O. Okay, so now to get H3O by itself, I've got to divide each side by this number. Now in my calculator, I have to put this in parentheses or it will not give me the right answer. Okay, so now this cancels out through division. So now I'm going to take 1 times 10 to the 14th, or sorry, to the negative 14th, 1 times 10 to the negative 14th, and I'm going to divide by 5 times 10 to the negative 8, that in parentheses. And now my H3O is it gives me 0.00000002. So 1, 2, 3, 4, 5, 6, 7. It is 2 times 10 to the negative 7. All right, so then you have to look at this and say, ooh, I wonder if that's an acid or a base. Well, which one do I have more of? Is this number more, or is this number more? Well, if you look, this is actually a smaller number. That negative 8 is smaller. So this one would actually be an acidic solution because my H3O is larger. So it's slightly acidic. I don't think there's a huge difference in this one, but it is slightly more acidic because of that. All right, so let's look at the learning check then. If lemon juice has an H3O of 2 times 10 to the negative 3rd, what is the OH? So we're going to set this up again just like we did. 1 times 10 to the negative 14th equals, I'm going to go ahead and plug this in, 2 times 10 to the negative 3rd times, I'm looking for OH. So even though it's a different type of problem, they gave me H3O, and if you're giving me OH, it's still the same thing. So I'm going to divide by 2 times 10 to the negative 3rd. Remember, I have to put this, once again, I have to put this in parentheses for me. This would cancel out. Now I'm going to get my calculator and do 1 times 10 to the negative 14th divided by 2 times 10 to the negative 3rd. And that will give me my OH 5 times 10 to the negative 12. Once again, that's a very small number. This is a small number, but not as small. And it is, look at this, it's lemon juice. So yes, that is quite the difference. Negative 3 to negative 12, this is tiny. This negative 12 is tiny, so this would be acidic. Okay, once again, I'm looking at my superscript here and those numbers. Remember, negative 3 is closer to 0 than negative 12 is. That's just super tiny. All right, so let's look at the last learning check. The OH of ammonia solution is 4 times 10 to the negative 12. So we're doing the exact same thing we just did. Remember, all of these have to equal 1 times 10 to the 14th. This combination has to equal that. So I have 4 times 10 to the negative 2nd. Now that's not a very, yes, it's a small number, but in terms of what we're dealing with, it's not that small. So I'm going to be surprised if this is an acid. I'll be surprised if it is. But let's check it out. So I'm looking for my I'm sorry. I'm looking for my H3O. All right, so I'm going to divide by 4 times 10 to the negative 2nd. That cancels out, leaving me my H3O. I'm going to plug this into my calculator. 4 times 10 to the negative second. Yeah, so my H3O equals 2.5 times 10 to the negative 13. That is super tiny. There is not a lot of acid in that. So this would be basic. So remember, once again, what I am comparing is I'm comparing these two numbers. Yes, it's a negative, so it's small, but this is way smaller. There's hardly any H3O at all in that. It is mostly base. So that's how I know it's basic, because that -2 is actually larger than -13. So I have more OH, which means that's a base. All right, so that is how you will then do your worksheet. If you look here real quick, I'll pull it up. The worksheet is doing the same thing. Right here, indicate whether the following are acidic, basic, or neutral solutions. Well, I have to figure out what my OH is. Once I figure out the OH, I can do that and be like, ooh, this is my acid's got -5. What's my OH have? Is it smaller? Is it bigger? If this is the larger number, then it's acidic. If this is my smaller of the numbers, that's going to be basic then. And then number 4 and number 5 are just calculating, like here's coffee. This is the OH, what's the H3O? So it's doing the exact same math we have done through the learning checks and the example. All right, if you need anything, you know Thursday if you come in that I will help you out. All right, if you need anything, just send me an email and let me know. Bye.